other hand, we don't know if the people will come or not. So imagine if we waste time waiting for people and they're not even here. They're not going to join us. So can I just say, let us proceed. Those who are here for the lecture, and then if those who wants to join late, they will do so. Okay, so your test is Monday, 22nd November, 10 o'clock. From the time that I got from your class group is 10 o'clock. And the venues will definitely be our labs, first year labs, both of them. And I think one of the third year labs. So this is what I will do. But I will send all this information to Colin. So because you guys are senior people, I don't think we'll have a problem with that. I will divide you into 3 according to your student numbers from the list that I will get from Dr. Mdele. Then I will send to Colin so that on that day you know where to go. So you just look for your name and then the lab number. Then you go to that lab number. That particular lab, instead of us going up and down and whatnot. So let's make it very organized and professional. So I don't think I will expect, if your student number starts with 19, for instance, when I say go to second year floor and I'll find you in the first year floor, in the first year lab. So we shall do it that way. Okay, I think that is done. So now let's continue from where we left yesterday. We were on this slide. Can you all see my slides? Let me start there. And can you all see what's in the slide? Because yesterday I think there were some.
Yeah, we can see.
All right, thank you. Thank you very much. Okay, yeah. So this is where we left yesterday. The 2 polycyclic heterocycles. It's the quinoline and the isoquinoline. So this we've looked at them before, and by now you even know how to number them, where it's position 1, number 2, number 3, number 4, and so forth. So if you were to be asked to name any analog of quinoline or any analog of isoquinoline, I'm thinking that it's something that which you can do without a struggle. Okay, so now we need to look at the electrophilic aromatic substitutions of quinoline and isoquinoline. Okay, so we say that the reaction found to be happening on benzene and not on the pyridine ring. Okay, so this is
Colin, Wi-Fi yo to shava ne?
Ya dumbulan taga sunga bosha wannan network ga gaisha da kafin.
Campus na mudagasi so na Wi-Fi yo shava pa yo to ṱuwa zwino.
Guys, sorry about that. The network has been restored, so I think we can proceed. Can you hear me?
Yes, ma'am.
All right, thanks a lot. Yeah, I'm sorry about that. I think it just came back. So let me just share my slides once again, and then okay, can you see the slides? Just let me know so that we can. No, it's not around. Okay, yes, just let me know so that we can proceed.
Yes, can see your slides.
All right, thank you. Okay, I need to start again. Yes, so I was saying that the electrophilic aromatic substitution, remember here now we are talking about quinoline and isoquinoline. The particular reaction, or not necessarily particular, but the substitution reaction, we say that it has been found to be happening on the benzene ring and not on the pyridine ring. Okay, so ding ding ding, it must ring in your in your minds that the isoquinoline and the quinoline, they are polycyclic, so meaning that they have two rings, unlike when you have a pyridine, which is just a monocyclic ring. Okay, so obviously the reaction will take place on the very same ring, but then when you have two rings, for instance, on these two ones that we are talking about, so you take note that the reaction will not happen on the pyridine ring, but on the benzene ring. Okay, what do we mean by that? For instance, for the nitration reaction, okay, so bear in mind that as much as is the nitration reaction, this is electrophilic substitution. So you are going to have the reaction that favors two positions, position number 5 and position number 8. Okay, so let's look at that. Right, there you are, wherein you have quinoline reacting with nitric acid in the presence of sulfuric acid. The reaction takes place at very low temperatures for about 30 minutes. What you will get is the NO2 being substituted at position number 5, right? That's what we said. It favors two positions, and the positions are on the benzene ring. So you take note of two things. All right. Number 1, at the benzene ring. Number 2, positions where the reaction or the substitution will take place at position number 5 and position number 8. And this can only happen if indeed you know. You see, how do you label your positioning? I remember Colin used to make a mistake saying carbon number 1. So he will start by from the nitrogen going to the carbon next to the nitrogen, saying that's 1. You see, if you do that kind of a mistake, so obviously even your substitution will be substituted at the wrong position. So it is up to you to make sure that from the previous slides when we were doing the naming of these heterocyclic compounds that you are very sure of your naming of the positions or the positioning of your compounds. So here you have the nitration at position number 5, which it's about 52% of the product. So it's almost, can you all see the slides? So people, can you can't see the slides now? Or it's just beauty?
No, I can see the slide now. I don't know about others.
Kateko, can you see the slides? Kateko is not there. Mashaka, can you see the slides?
We cannot.
Yes.
Yes, I
Mashaka,
can see the slide, but it's not moving.
it's not moving. What do you mean it's not moving? Okay, Maite, which slides are you now? I mean, what can you see on the slide now?
The one with 1 nitration.
Yes, and you can see the reaction scheme, right?
Yes, ma'am.
Okay.
Myself, I'm seeing the first page. I
The
don't know
first-
if it's, yeah.
The first page. You mean the first
Yes.
slide?
Yeah, the first slide.
The first slide.
Yes.
Like,
I don't know if it's my network.
oh no. I think it's your network. As in like slide number 1
Yes.
of the whole
Slide
presentation.
number 1.
Okay, yeah, it's probably your network, but let me just try to do this again, right? Let me try to share it again and then see how
Can you try
guys,
to go back and forth and see if the ones?
if it won't move. Okay.
Yes.
Okay, let me just go back. Okay. Well, what do you got? I want the one who said he only sees the first slide. What do you see now?
It's still not moving. Maybe it's my network. If you can proceed, I will access the recording class.
Okay.
Recorded class.
Okay, thank you. The rest of you, can you see the mechanism that we looked at yesterday of the halopyridine? All right. Okay.
Yes.
All right, thank you. Let's just, okay, let me just go straight. Yes. So as you can see, the favor in between the two positions, it's almost, it's not 50-50, but it's almost, it's not like one, it's more significantly more than the other. 52% of the product of the nitro or nitration happening at position 5, and 48% wherein the nitration happened at position 8. Okay, so this is something which you really need to remember at all the times. Okay, now with the isoquinoline, okay, the very same nitration reaction of the isoquinoline. Remember, with the quinoline, the positions are 5 and 8, but with the isoquinoline, the reaction will favor position 5. Okay, if you look at the two products, if you look at the products that are given there, it's like 9:1 or 90%, and the other one is just 1. So it's close to even maybe not happening. Okay, so you can see that the favored position for the isoquinoline, for the nitration substitution, it is at position number 5. Okay, so this is something which you need to remember at all the times, that the reaction between the two polycyclic heterocycles, for instance, your quinoline and isoquinoline, right? The electrophilic aromatic substitution, in particular the nitration reactions or nitration substitution of the two. For the quinoline one, the reaction will favor position 5 and 8, and while the isoquinoline one, the reaction will favor position number 5. Okay, so now let's look at another type of electrophilic substitution. In this case, for instance, sulfonation and halogenation. Okay, we say that, you know, the sulfonation with 30% oleum. Has any one of you ever heard of that oleum? Anyone? You can just say yes or no. If you've heard of, you know, kind of a reaction wherein you need about 30% of that oleum. Anyone? Maite, have you ever heard of that kind of a reagent called oleum?
No, ma'am.
All right. Okay. So this kind of reaction, or this particular reaction, so you would be having your, for instance, your quinoline, right? And a fuming, so this will mean that it's a fuming sulfuric acid in the presence of sulfur trioxide. So that is what oleum is. I hope today you've learned something. So you will need about 30% of that. So it's a 30% of your fuming sulfuric acid in the presence of sulfur trioxide. When you have that kind of a reaction, you know, the sulfonation will favor position 8 in quinoline and position 5 in isoquinoline. Okay, so if you can remember that with the nitration, we said on the quinoline one, the two positions are favored, 5 and 8. But in the isoquinoline, it's only 5. But when you do the sulfonation, right, on the quinoline, position 8, and on the isoquinoline, position 5. That's where the reaction will take place. And with the halogenation, the halogenation favors positions 5 and 8 in quinoline and position 5 in isoquinoline. So your halogenation, halogenation reaction is the same as the nitration reaction. Okay, so this is something that I'm hoping you will never forget, regardless of how. Okay, take note of this, regardless of how you are being asked. Okay, this is this information should just stay with you, so that you don't get confused, you don't get the question wrong. Okay, so now if we look at remember we looked at the reactions, their reactions, how do they react in terms of the substitution or halogenation or and. But then if you need to make them, if you need to, I mean, making them, I'm simply meaning in an organic term, a synthesis. How do you prepare aromatic heterocyclics? So how do we prepare pyrrole, for instance? How do we prepare thiophene, for instance? How do you prepare furan? By now, I'm hoping that you know what is pyrrole, what is the structure, how does it look like? It's a 5-membered ring with thiophene, it's a 5-membered ring with as a heteroatom. Furan, it's a 5-membered ring with as your heteroatom. So those are some of the things that you can never forget. Okay, so if you consider a retrosynthesis, we've done retrosynthesis, right, guys? When I'm talking about retrosynthesis, this is not something which you are like, oh gosh, what is that? Okay, I need just someone to unmute your mic and say, yes, we've done retrosynthesis of many reactions and we understand what the term is. Can I get a volunteer?
It's a reaction which is reversed.
A reaction which is reversed. Okay, so it would mean that starting from the product going all the way to your substrate or to your starting material. Okay, so if we consider the retrosynthesis of, you see, X, you know, this is a 5-membered ring with an X. So X can be NH, S can be X can be S. For thiophene, SX can be oxygen. Okay, so if you look at the retrosynthesis, so this is if, for instance, that is your final product, that is your furan, for instance, and you have carbon-oxygen bond cleavage. So this in the middle, I don't know if when I do the highlight, you can see that this in the middle is what you would expect to get. Okay, so there's a bond breakage between your carbon and your oxygen or your NH or your sulfur. Okay, and then what would be your starting material? It will look like that. Okay, remember R1 or R2 can be anything, can be hydrogens or can just be anything. Okay, anything which is substituted there. All right, but if we speak particularly about pyrrole or thiophene or furan, you would remember that your R1 or R2 is simply hydrogens. Okay, so hence, now we know that we can use 1.4 diketones, right? Because that is what you can start with. If you look at the retrosynthesis that we just looked at from this reaction scheme, which is there in front of you. From your product, you can go all the way to the starting material, which now we can see that it's actually 1.2 diketone. Okay, because if you have the bond cleavage between your carbon and your atom, whether it's a carbon, a nitrogen, a sulfur, and oxygen, it would take you to the first monoketone, and if you cleave on the other side, you will now get the 2, which will now be labeled or named 1.4 because now the ketones are at position number 1 and position number 4 to synthesize furan, pyrrole, and thiophene. Okay, so for instance, firstly, if we need to synthesize pyrrole, right, you would need 1.2 ketone, 1.4, excuse me, diketone, right, in the presence of ammonia. That is very important. That would result in you having pyrrole. Okay, in the presence of ammonia, it will give you a pyrrole. When you have an acid, for instance, okay, that will give you, and you have the very same 1.4 diketone. So for instance, if you have 1.4 diketone, a lot of it, right, you divide it into 3. So you weigh, for instance, you're in the lab, you weigh 1 gram to one flask, round bottom flask, you weigh 1 gram to another round bottom flask, you name it number 2 or second reaction, you weigh another 1 gram to another flask, which is flask number 3, right? You put them in such a way that they are ready, okay? To number 1, you add ammonia. To number 2, you add an acid, okay? So clearly you are going to get 2 in this instance, 2 different compounds. To the one that you would have added ammonia, it will give you a pyrrole. To the second one, which you would have added an acid, it will give you furan. And lastly, if you need to to synthesize thiophene, you will need what we call Lawson reagent. Lawson reagent. So Lawson reagent, you might not have seen it before, but this is how it looks like. Okay, so as you can see, is P2S5, and someone might already asking themselves the question, but then how is that reagent even being synthesized? I'm sure it's called Lawson reagent because it was discovered by this guy or a lady. So it would be the reaction between, your methoxybenzene and phosphorus pentasulfide. Okay, so he probably just added those two, methoxybenzene and phosphorus pentasulfide, and boom, he got a reagent. I'm thinking it made it through to the researchers, because with this reagent, you are able to convert the oxygen, right? Remember that the two oxygens of the ketones, the oxygen functionalities to their thioanalogues. And as you can see, we do have a thioanalog in this instance. Now our product is thiophene. So when you have a ketone, you throw in what you call Lawson reagent, you are expecting to get a thio somewhere. Okay, hence the use or the discovery of this reagent was very important. So this is how the reagent looks like. Very easy. I mean, it looks so easy, but then see, I mean, its function or how it reacts with the ketones is very, very important. Okay, so this is how you basically synthesize the two heterocycles. I mean, the three heterocycles. Your pyrrole. You know that the presence of ammonia. It's very important to make sure that you get the NH there. The acid. You know that it's very important so that you can get the furan, the O there. As far as the thioanalog in this instance is the thiophene, it's very important that you use the Lawson reagent. And as you can see that all of them, the starting materials are the same, 1.4 diketones. Okay, any question? Nothing. All right, let's continue. So the other, alternative synthesis routes, it might include what is called the Gewalt reaction. Now this in particular is for the thiophene synthesis. Okay, so remember that as much as we've seen that you can use the 1.4 diketone in the presence of Lawson reagent to give you thiophene. So someone else discovered and named that particular reaction after their name, Gewalt. Okay, and this is how his was done. Okay, so you look at the two reagents there, right? Already, I'm thinking what comes into your mind or what you are in particular looking at, which is very important, are the functional groups. So you're looking at, but then how, why, this is this and that, and it gives you the thiophene analog. Okay, so for instance, the first reagent, no, not the reagent, but the first substrate there, the first starting material, because we have plus the first one. What functional group is that? So you have R1 that is bonded to carbon, double bond oxygen, bonded to R2. Remember, R1 and R2 can be anything. Okay, so what functional group is that?
It's a ketone.
It's come again?
It's a ketone.
A ketone, right? Okay, so let's look at the second one. What is reacting with? Okay, any take?
Ester.
Hmm? Come again? Say it again.
The nitrile ester is one.
It's a say it again.
It's an ester.
Okay, you do have an ester. I agree. Right? What else?
The nitrile ester.
Nitrile. Okay. And then boom, there you go. In the presence of S8. What is S8? Aye, guys. What is S8? You mean like you from first year up to now, third year, organic, inorganic, physical, analytical. You've never seen S8 before. And the class goes quiet. And I won't proceed. This time I won't proceed. What is S8?
It's octasulfur. It's octasulfur.
Octasulfur. I like that. Octasulfur because because of 8.
Yes, because it's joined by single bonds. All the sulfur. Yeah.
all the sulfurs, 8 of them are joined by the single bond. Anyone? Thank you. Anyone who wants to try that? It's not even trying. But like I'm saying, guys, have you? So this is for the first time you see this S8.
Yeah.
No. I do not believe that. Wavuti, I do not believe that. From first year until today, you've never seen S8. Okay, tell the truth. If you've seen it, but you just don't know what it is, maybe say so. Not that you've never. Even in inorganic. You can't be quiet. Humbelani, Quinta.
You just didn't.
You just didn't?
We were not exposed to it like other compounds. But it's just theoretical.
You've never, okay, you were not exposed to it. I like the way you're saying it. You were not exposed to it. So are you speaking for yourself for in general for everyone?
I'm for myself.
Thank you so much. You're speaking for yourself. Humbelani Quinta. How I miss physical classes because someone just keeps quiet, like they cannot see me. So what? That's Humbelani. Ifi Lukeli.
They are sleeping, those ones.
Hello. Oh, okay. Yeah, there is Ifi. Ifi's not sleepy. Yes, Ifi. What is S8?
S8.
S8.
Isn't it sulfate?
Isn't it?
Octasulfate.
Isn't it sulfate? Yes, I can hear you say that again.
Octasulfur.
You said octasulfur.
Yeah, I think so. I'm not sure.
You think so? You're not sure. Can we have a savior?
Ma'am, can I try?
Please.
Octathiocate. Cane.
Octa.
Thiocane.
Thiocade. Thiocade. No, Matemba, did you just say thiocade?
Thiocane.
Thiocane.
Yes, ma'am.
Wow. Okay, thank you. Switch off your mic. Yes, anyone? Anyone else?
Ma'am, I think octafluorocane and the octasulfur are the same thing.
The same thing. So what is this cane? What is this cane?
I think.
You think?
Oh, I wanted to confirm up on the structure, since the structure it has it can be written as a ring, so it can also be a conformer for cyclo. Cyclo can be the name can also start with cyclo.
So it would be cyclo what?
Octasulfur.
Cyclooctasulfur. Wow. Yeah. We have chemists in the chemistry department. Okay. So if I may ask, sulfur. Okay. I don't know if you have periodic tables in front of you. So if you don't have, but this is something which I'm thinking by now you know. Okay, you've done periodic table for quite some time now. Sulfur, right? How does it look like? Or this, let me say, if I were to say to you, write would it now be the molecular formula of sulfur? How would you write it? So let me say, I'm just giving a wild example. Sulfur reacting with chlorine. Okay, and I say to you, write the chemical reaction. I would have written them in words. Sulfur reacting with chlorine. Okay, how would you write that chemical reaction? This is what we teach you in 1540 or 1140. Write the chemical reaction between what and what. In this instance, I'm saying between sulfur and chlorine. Anyone? Beauty? Okay, sorry, Mamba.
Is it
Yes.
not SCL?
Cl? You say C?
SCL.
No. Not the product. I want you to write the chemical reaction. So it would be the two reactants that I've just spoken about. Don't worry about the product per se. Yes, it will be.
Oh, it's going to be S plus CL. Just but
that. But
since CL it's a diatom, it's a diatomic molecule. It may be S plus Cl2.
S plus Cl2. Can I, for the sake of time, some of these things, when you, I'm hoping you are doing this, guys, because besides the fact that you guys are third years, you after this, then that's it as far as undergrad is concerned. Things like this, myself, then I would go after this lecture, I will go and really check what is this S80. Instead of just saying, I don't know, I did not know, I don't care, that's it. Okay. So this is called, I mean, this is learning. It would mean that you really you care about, you know, the things that you learn in class. It might be that you've never seen it, like Leonard was saying, I've never been exposed to, but now that you've seen it, can't you make it up to you to go and check what is this S8? Okay.
All right.
Okay. Thank you. Okay. So now, as you know, I know most students, they hate this. I don't know. I hope you guys, you have improved. But I know from first year that first year students, they hate reaction mechanisms. Second year is the same. It's a struggle. So with you guys, I'm yet to see. So now the reaction mechanism, come again?
Is that the Michael's reaction?
The
Michael reaction.
Michael.
Yes, from Aldo reaction.
Yes, tell us more. Well done. Tell us more. Tell us more, Colin.
Yeah, isn't that in Michael's reaction we have a donor?
So in this
and
instance,
also etc.
Okay. In this instance, which one is the donor? I like the fact that they are in different colors, so you can just say the what color.
The blue one is the donor.
The blue one is
it lost the electron.
It is yes.
So it's a nucleophilic.
It's a nucleophilic. Okay. Very, very important. If I take you back, right? Okay, so look at the two reactants very, very, very careful, especially the second one, which had the nitrile group. Okay, because that is where now you end up having a nucleophile. Okay, you look at it as it is. Let's go. There. What happened to it? What happened? There's a step that occurred, which is not shown here. Okay.
I think they reacted it with the base, then they removed the acidic proton.
So yeah, well done. What was removed was the acidic proton. Okay. Why are you saying that proton is the acidic one?
Because it's next to the electron withdrawing groups, double bond O and the nitrile.
All right. Okay. Well done. Okay. So, but can you see this step which we are talking about is not shown to you? Okay. So obviously it's because, like we say, you are now at the higher level. You know that the first thing that will happen, because you cannot come to me and say from nowhere where I did not see you doing that first step wherein the proton was abstracted. Okay, so that has happened. That is the first thing that happens on this reaction mechanism. And now you have a nucleophile. We know that a nucleophile is electron rich. It will donate electrons. It will attack in this instance. Now the red one, which is electrophile. Remember, with the C double bond oxygen, like we've taught you in first year on the introduction to the organic reactions, the carbon or the oxygen either can be electrophile or nucleophile, depending on what it reacts with. Okay, so in this instance, because yes.
I think in future you should mention these things so that it doesn't confuse. For instance, here you should have said the alcohol before the water was removed.
The alcohol.
Yeah,
What alcohol?
isn't on that when that electrophilic is gonna attack that O. It's gonna form OH that is gonna be removed.
Okay, say that again. When this
Electrophilic attack on the oxygen,
on the oxygen,
on the double bond O.
the attack is on the double bond O, Colin.
On the carbon with the double, yes.
Yeah, yes, on the carbon.
Yes, on the carbon with double bond O.
Yes, yes. So what?
Isn't the intermediate supposed to have the OH?
The intermediate.
Then, yeah, before we remove it, we remove
the water. We removed this water. Yes. Okay.
Yeah, I mean, you should show those intermediates what's gonna happen.
Colin. Okay. But then, okay, it's fine. I get what you're saying. It's okay. We are now over time. Yeah, these lectures are very slow for my liking. So I'm hoping next week, indeed, we must finish. The first one we will push very, very fast. Not like very, very fast, but then we will go in such a way that we don't end up not finishing, because if we don't finish, then which means, going to the test week, we'll have a problem. But yeah, I'm hoping that we can keep the time. Your point is taken, Colin. So thank you very much. Let's meet again next week on Wednesday. Please, guys, make sure that when you come here, you have all this background, you read, you have these slides by now, but then have that, that information, and the things that you were not aware of, look for them. This is organic chemistry. It is easy. It's easy of the four, but depending on how you look at it. Okay, depending on how you look at it, it's for me, I think it's the easiest, because it is what it is. You can never, for instance, between these two reactions, you can never say that this blue will attack the carbon on the carbon adjacent to R1. You see, for instance. So that's why I'm saying it's easy. You just need to know where, how, when, how, why, in terms of the reactions of or the reaction mechanism of any kind of a reaction. Okay, so with that, sorry for going over time. I will see you again next week on Wednesday. Thank you. Bye.